In this lesson, we're going to bring together everything we've been building about electron structure and use it to explain the patterns we see across the periodic table. If you think about a circus, there isn't just one act happening at a time. You might have acrobats in the air, jugglers on stage, and a ringmaster directing attention, all working together to create the overall performance. In a similar way, the properties of elements aren't controlled by just one factor. Several forces are at work simultaneously that affect the properties of a specific element. By the end of this lesson, you should be able to look at an element's position on the periodic table and predict its relative size, how strongly it holds on to electrons, how strongly it attracts electrons in a bond, and how reactive it is, all by understanding the acts happening behind the scenes. There are several atomic properties that follow clear patterns across periods and down groups. The big ones for today: atomic radius. You can see the arrows point in the direction at which it increases. Ionization energy and electron affinity, they follow the same trend. And electronegativity also increases as you go left to right, bottom to top. Metallic and nonmetallic character refer to how reactive they are. As you can see from looking at this image, fluorine is the greatest nonmetallic character. That means that it is the most reactive of the nonmetals. Metallic character, reactivity, increases as you get closer and closer to francium. And as we go through this, I will be mentioning different benchmarks. So, largest and most metallic, francium. So then we go ahead and we start our little video. I have a video and I'm going to talk about how these different forces such as shielding and effective nuclear charge interact in order to affect the ionization energy and the reactivity of the different alkali metals. I also have reaction clips of the alkali metals with water that were conducted by OpenLearn from the Open University. Let's look at how shielding and increasing effective nuclear charge affect the reactivity of the alkali metals. As we move down the alkali metals, something important changes. Each element adds another energy level. That means the valence electron is farther from the nucleus, and there are more inner electrons in between. Those inner electrons create shielding. We can describe this mathematically using effective nuclear charge. In the equation shown on the screen, Z is the number of protons, so it's the atomic number, and S represents shielding. So effective nuclear charge, Zₑff, is the net pull felt by the outer electron. Notice what happens to the values for nuclear charge and shielding as you go down the group. Z increases from 3 to 55, but shielding increases dramatically, from about 2 to about 50. So even though the nucleus becomes more positive, most of that extra pull is canceled by shielding from the core electrons. Notice, however, that the effective nuclear charge increases only slightly. Meanwhile, the distance separating the valence electron from the positive charge of the nucleus has increased so that the valence electron in cesium is roughly 2 to 3 times farther away from the nucleus than it is in lithium. Ionization energy, IE, is the amount of energy required to remove an electron from an atom or an ion. Ionization energy depends on two major factors: how strongly the nucleus pulls on the electron, which is determined by the effective nuclear charge, and how far away the electron is, given by the principal quantum number, n. As we go down the group, n increases from 2 to 6. And because the electron is farther away and heavily shielded, the ionization energy drops. Lower ionization energy means the electron is easier to remove. And that's why reactivity increases as you move down the alkali metals. It's not because the nucleus is weaker, but because the shielding and distance make the outer electron easier to lose. Reactivity isn't random. It's the balance between nuclear charge, shielding, and distance.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
As you just saw, shielding and increasing effective nuclear charge affect the properties of the elements. One of the trends that seems to give students the most trouble is the change in atomic radius. It's not the first one that gives them the trouble, when the fact that it gets bigger as you go from top to bottom. That one kind of makes sense because you have more energy levels. It's the fact that it decreases as you go from left to right, and that change is due to increasing effective nuclear charge. And here we have our benchmark for the largest atom is going to be francium, and the smallest atom is helium. So shielding effect, I know I've referenced it several times already. This is kind of a silly way to kind of look at it a little bit more closely. So what it is in its simplest level is that the inner electron shells insulate the valence electrons from experiencing the full electrostatic attraction with the nucleus. So we're going to start out. We have our positive nucleus and we have our one valence electron. So this is sort of like hydrogen. And there is nothing interfering with that valence electron from experiencing the full attraction to the nucleus. So hydrogen's electron is held very tightly. As we move down the group, and I didn't actually get it right because I should have increased the number of protons in here, we get more. We have core electrons as we go down across each period. We get more electrons. There we go. And so the valence electron is experiencing very little of that nuclear charge. And so if there's anything that comes by that's even slightly more positive, the valence electron will be lost. So it's easy for it to be lost. It has a low ionization energy. All right, so increasing effective nuclear charge, this is the one that gives people a little bit more trouble. So here we have lithium. So we have our 3 protons in the nucleus. We have our 2 1s electrons. So they're going to be the core electrons. And then we have our 1 valence electron. So there's a certain amount of interaction going on between the nucleus and the valence electron. If you go across the period to nitrogen, you have more protons. You have more valence electrons, but you still just have those 2 core electrons. The valence electrons do not shield each other from experiencing the charge of the nucleus because they're all in the same energy level. And so as a result of this, each valence electron is going to get pulled in closer to the nucleus because the electrostatic attraction is higher.
Uh-oh.
So this is why they get smaller as you go, atoms get smaller as you go from left to right across a period. All right, so you have to consider that the size of an atom is mostly determined by the number of electrons around the nucleus. Remember, Rutherford said that the atom consists mostly of empty space. And so we have the nucleus, this tiny, tiny nucleus, and then miles worth of distance, if we're going to kind of think in terms of our own reality, before you start hitting the electrons. So the more electrons you have, the more space that particular atom is going to take up. So in this picture, we have the neutral atoms are shown in gray, and then the ions that they form are shown in red if it's a cation, it loses electrons, or in blue if it's an anion. So you can see that for the metals that form cations, the ion is smaller. And it's not just a little bit smaller, it's a lot smaller, just from losing a couple of electrons. If you notice boron, which has lost 3 electrons, the cation is much smaller than the lithium ion. Now if you go the other way and you start adding electrons, it gets bigger because you're adding more electrons. So in the case of oxygen, well, let's do fluorine first. In the case of fluorine, you add 1 electron and it goes from 71 picometers to 119 picometers as far as the diameter goes. If you notice, again, if you add just 1 more electron, in case you get the oxygen anion, then it goes from 73 as the atom to 126. So those electrons make a big difference. So the thing to remember is that size increases as a negative charge increases. So ionization energy, this is linked to how reactive something is, especially for metals, because metals, what characterizes them as being a metal is that they form cations. So it's defined as being the energy required to remove an electron from a neutral atom in the gaseous state. So if you have a high ionization energy, that means you have a large amount of energy required. So things like the noble gases or the halogens, they don't want to be cations, so they're going to have a high ionization energy. Helium has the highest ionization energy, that's your benchmark, and it increases as you go left to right, bottom to top. And so here I have an image just illustrating the ionization of lithium. So you start out, there's too many rings on my lithium. So we're going to ionize this 1 valence electron, and afterwards we have a lithium ion in the gaseous state and the electron. And it takes 520 kilojoules per mole in order to do that. If you go down to potassium, it's going to be, sodium, it's going to be a little bit smaller because ionization energy decreases as you go down a group. So electron affinity is similar to ionization energy, except it's more related to elements that want to form anions. So electron affinity is the amount of energy released when an electron is added to a neutral atom. So ionization energy, we are removing an electron. Electron affinity, we are adding an electron. So hit click, there we go. So if you have something like fluorine, it has a very high electron affinity. You allow it to completely fill that 2s shell, which is why it gets so much stability from that. So electron affinity increases as you go left to right, bottom to top. And then our benchmark for electron affinity is going to be fluorine. And so here we have the electron affinity of chlorine. We're just adding electrons. So we start out, we have, oh dear, my diagram's not right. There should be 7 valence electrons on this chlorine atom. And then we add another electron to it. Now we have the complete shell is filled up. And we have a chloride ion in the gaseous state. And this process releases negative 349 kilojoules per mole. Both the ionization energy and the electron and affinity trends are due to increasing effective nuclear charge, and which gives you the smaller atomic radius. So electronegativity is another trend that you can predict from looking at the periodic table, but it is a little bit more important when we start talking about bonding than it is at this particular moment, but since we're talking about trends, we're going to throw this in. So the symbol that is given to electronegativity is chi, and it is the ability of an atom to attract electrons when it's in a chemical bond. Typically, people don't calculate it, but if you really, really wanted to, chi is equal to ionization energy plus electron affinity divided by 2. And if you think about it, if you have a high ionization energy, it does not want to lose electrons, it wants to keep them. And likewise, high electron affinity, it wants to keep them. So we're adding to the factors that want to keep those electrons near that nucleus. So the benchmark is fluorine. It is the element with the highest electronegativity. Increases as you go across a period, decreases down a group. The reason why this matters, like I said, it has to do with when you start talking about bonding, is that you can end up with polar bonds and polar molecules when you have large electronegativity differences. And these polar bonds and polar molecules have a huge impact on the physical properties of the substance that they are in. So just so you can understand the diagrams, so oxygen has an electronegativity of about 3.6 or 3, I can't remember exactly. And then hydrogen's way over on the other side of the table. It has a electronegativity value of about 2. And so the electrons are going to spend more of their time around the oxygen than they are around the hydrogen. Since we have now polarized our electron cloud, we end up with a permanent positive charge on the hydrogens and a permanent small negative charge on the oxygen. So when you have the substance in the bulk phase, the molecules are going to want to stick together. So we have the small positive charge on hydrogen is forming an intermolecular hydrogen bond with an adjacent water molecule's oxygen. This is why water, for example, has such a high surface tension, because those molecules are stuck together. So here's some of the values. So let me see. All right, so fluorine is 3.98, oxygen was 3.4, not 3.6. Hydrogen, about 2, like I said. You can see we got some spikes in here, but for the most part, the closer you get to fluorine, the more electronegative it is. Notice that we have electronegativity values for krypton, xenon, and radon. This is because they have been able to make compounds with them when you react them with fluorine. That's because fluorine is so reactive. And this was first demonstrated that the group 18 elements were not inert. They were, in fact, noble. They don't like reacting, but they will in some cases, in 1962. And so the first one that was discovered was xenon fluoride, and then krypton fluoride. They also have some oxides of these compounds. I'm not familiar with the radon chemistry, but I'm sure that came around about the same time. They have not been able to make compounds with argon, neon, or helium because those atoms, the electrons are so tightly held that even fluorine can't disrupt those shells and make them form bonds. Oh, I got my trend. Electronegativity increases as you get closer and closer to fluorine. So phosphorus, for the last part of this lesson, we'll be wrapping up our discussion of the periodic table. One of the more interesting elements is phosphorus, and I thought I'd throw in the recipe that an alchemist, Henning Brand, used to isolate elemental phosphorus in 1669. The alchemist wasn't looking for phosphorus. Instead, he was looking for a way to prepare the philosopher's stone. So this was kind of like a happy accident. So the recipe was, we take the water, evaporate the water out of 60 gallons of human urine. Had to be human because they were convinced, the alchemists were convinced, that there was some sort of vital essence in living organisms like humans. And then you heat to the 10 pounds of dry stuff that you get after you evaporate all the water in a glassmaker's furnace. The key thing about a glassmaker's furnace is it can exclude oxygen, so you're not allowing any reactions to occur. We're just getting rid of all of the organic stuff that's in there. And you are left with 1 ounce of glowing solid phosphorus. So yes, phosphorus really is the P element. A little joke. All right, so some more tidbits about just the periodic table. Most of the metals are silvery gray in color. There are some exceptions, like copper and gold, which are the reason why they have their characteristic colors is because of the energy levels of their d electrons. It allows them to hop around, and they can absorb some of the wavelengths of visible light, which then means that some color is being reflected. That's why they have their color. We also have nonmetals that have characteristic colors. Sulfur is a brittle nonmetal solid. Phosphorus comes in 2 different colors. We have red phosphorus, which is the tame stuff. If you want to do any kind of chemistry with phosphorus, elemental phosphorus, this is the stuff that you would use. And then there's the white phosphorus. This is the stuff that the alchemists discovered. White phosphorus is nasty, nasty stuff. If it is exposed to oxygen, you have to keep it under oil in order to keep it from reacting with oxygen. It catches on fire, and then once it starts burning, there isn't a whole lot you can do about it. They used to use phosphorus. Actually, they still do use white phosphorus in grenades, but the purpose now for the grenades is to create smoke screens. In the past, say World War II era, they were putting them in there so that white phosphorus in the grenades, so that when they threw a grenade at people, either the grenade would hurt the people, or the phosphorus would catch them on fire. It was one way you got your enemies one way or the other. Thankfully, that has now been banned. The halogens also have characteristic colors. So fluorine, a highly reactive pale yellow gas. Chlorine, also fairly reactive, light green gas. Bromine, because now it's getting kind of heavy, is a dark orange to dark red liquid, but it really, really wants to be a gas. It doesn't have a whole lot keeping it in the liquid state, and so there's always a red haze above it. And then iodine is a dark violet, it looks black, crystal, and it also would much rather be a gas. So there's not a whole lot keeping it in the solid state, and so it sublimes and makes the purple haze that is above iodine solid. So the very last bit would be allotropes, just a vocabulary term. So allotropes, remember we had isotopes, so they were the same element with different mass numbers. So allotropes are the same element but with different structural forms. So, for example, in your pencil, the graphite, it's not lead, it consists of carbon atoms all bonded together in sort of a honeycomb fashion. And then they form sheets of graphite layered on top of each other. So when you are writing with your pencil, what you're doing is you're rubbing sheets of those honeycomb carbon atoms off onto your paper. Then we have diamond. This is carbon that is bonded together in a 3-dimensional lattice. This is why diamond is so hard, because it has that 3-dimensional, it's bonded every which way it can be. So when you apply pressure to it, all those bonds are resisting any kind of change. And then you have amorphous carbon. Charcoal briquettes is the only thing I can think of for this. And that's where you just have a whole bunch of carbon atoms all just smushed together. And that's why if you handle charcoal briquettes, you get carbon all over your hands, because they're not bonded together at all. There is another type, another allotrope of carbon. It's called, I'll get to that. In 1985, they discovered that they were looking at different types of soot, essentially. And they discovered that carbon will form essentially like these little atomic-sized soccer balls with 60 carbon atoms bonded together. Now, at the time, there was a architect who was making geodesic domes, and those domes had the same sort of basic structure. It was a combination of hexagons and pentagons that give it that unique shape. And this architect's name was Buckminster Fuller. So they decided, all right, we're going to name them after this architect. So they became Buckminster Fullerines. That's too hard to say. So C60 got the nickname of Buckyballs. And then after they knew to look for C60, they started to discover even more of them. And so they found that there was one that had 70 carbon atoms, looked kind of like a football, so they called it a Bucky football. And then they kept finding more and more. It turns out when you have soot, you got a whole bunch of these, they call them fullerenes, where it's got hexagons and pentagons, and they make different shapes. So that is just a little bit of a trivia as far as the fourth allotrope of carbon. All right, so to wrap up this lesson, periodic trends, and to wrap up this unit, periodic trends are driven by interaction between valence electrons and the nucleus. So atomic radius, ionization energy, electron affinity, and electronegativity are interconnected and follow predictable patterns across periods and down groups. Those were the arrows that we were talking about. Shielding increases as you go down a group, allowing valence electrons to be farther from the nucleus and more easily removed, so lower ionization energy. Effective nuclear charge increases across a period, pulling the electrons closer and strengthening the attraction. So that's going to increase the ionization energy and make them smaller. Reactivity depends on how easily atoms will gain or lose electrons. So if they are a nonmetal, they tend to gain electrons. If they are a metal, they tend to lose electrons. And the periodic table is a map of repeating patterns. And you can look at an element's position and be able to make predictions about its relative size, charge, bonding, and chemical behavior. So that's it for this lesson on periodic trends and for the unit on electron arrangements and periodicity. Thanks for listening.